Hello. So I hope my screen is visible. Can anybody confirm? Am I audible? Hello. Hello. Am I audible?
Yes, sir.
Okay. So today we will do some problems regarding week number 5 on quantum mechanics and molecular spectroscopy. Okay. So let's start. So in week number 5, you have learned about this um, lifetime tau, you know the process spontaneous emission. Like there are two states, let's say 1 and 2. So initially you gave some energy to this ground state particle. So all the particles in ground state, let's say n1, they got excited to the excited they got transferred to the excited state. Let's say the population is n2 in this second state. Now what you do, like you turn off the light, that means you don't supply any external energy to this system. Then in this case what will happen, this excited particles or excited electrons, they will jump to the ground state by emitting energy, right? So this kind of process is called spontaneous emission. Okay. So so this rate of transition, this depends on this rate of transition dn2. It depends on the population of this excited state. Let's say at time t equal to 0, n2 particles were there when light is turned off. At time t equal to 0, n2 is 0, and you know the spontaneous emission, it depends on Einstein coefficient a. Okay. So then if we do the integration, then we will get n2 t is equal to n2 0 e to the power minus at. Okay. This a now is called decay constant. Okay, let me write here. Okay, so a is now called decay constant, and we define lifetime tau as 1 over e, or let's say the time t equal to tau is equal to a. We define this, we take this time equal to this 1 over a, so that this function e to the power minus at, this will go minus a times 1 over a, so it will go to e to the power minus 1. So what will happen effectively? N2 0 by e, e to the power minus 1 is nothing but 1 over e, right? So we defined a time, we named it as tau, which is 1 over a. So at this time tau, what happens? The initial particles, they decay by 1 over e. This e is called natural number actually. So the time taken to decay this natural number of particles from excited state to ground state is called lifetime. Okay, so n2 tau by n1 0 is nothing but 1 over e. Okay, so this t is called lifetime. So we need to calculate the natural lifetime of the upper state of the spectroscopic transition of the spectra source peak with full width at half maximum. Okay, so in last class you learned about this line shape. So it peaks at some frequency, let's say omega naught, and it has a intensity I0. Okay, its amplitude is I0, and what happens at half intensity I0 over 2, we define the width as omega, and we call this is delta omega. We call this width as what we call this width?
Sir, line width.
Yes, yeah, thank you. So we call this as line width. Okay, so in last class we learnt about this also, the line width. This maybe the notation was like this: delta omega half, when it is defined at this half intensity position. So we define this as delta omega half. This is equal to 2 pi delta mu half. Okay, so this is angular. If you say this in frequency term, this is frequency, this is absolute frequency, this is absolute angular frequency, but we are defining width, so maybe its dimension will be in centimeter something. So we can, okay, you check this question. The width is defined as this centimeter inverse. Okay, so we have to rearrange this right hand side. So if I do like this, 2 pi c delta nu half. Now you see, if I multiply c is speed of light. Okay, so this is meter per second, and this is given in centimeter inverse. So this is centimeter inverse, or maybe you can say meter inverse. So effectively this will give me the unit second inverse. Okay, so how is this line width depends on this lifetime. So there is a formula for that. This okay, lifetime the natural lifetime this will be equal to 2 by omega delta omega half. Okay, so we need to estimate this lifetime, and we have the knowledge of this from this formula. Actually this is given, so from that we have to calculate this, and from that we can calculate this natural lifetime. Okay, so in this time what happens, the number of particles in excited state, they decrease by a factor of 1 over e. Okay, so let me apply this formula. This is 2 pi c delta nu half. Okay, so I have pi 3 is 3.14, c is in 3 into 10 to the power 8 meter per second, and this value for question A is given, delta nu half is given as 0.01 centimeter inverse. So I have to convert it to meter inverse, because I am writing speed of light in terms of meter per second. So this will be 0.01 times 10 to the power 2 meter inverse. Okay, so it's nothing but 1 meter inverse. Okay, so this is 1 meter inverse. This meter inverse meter cancels, so okay, I have space here. So this will be equal to 1 by 3.14 times 3 into 10 to the power 8, or 10 to the power 8 divided by 3.14 times 3. If you calculate this, it's like 9.3 or 4 2 9.42 10 to the power, sorry, this is minus 8, this is second. In denominator there was second inverse, so it's second. So if you divide this, it will be like 1.1 into 10 to the power minus 8. Okay, this maybe 0.1, so it will be minus 9 seconds. Okay, so did you understand this question? We are given this line width in terms of centimeter inverse, and from that we have to calculate this natural frequency. Okay, so this delta nu half, this is given, you need to calculate this tau lifetime, and we have a formula for that. Tau lifetime is 2 over delta omega half. Okay, this delta omega half is nothing but 2 pi. I have converted this to appropriate units, that's why I multiplied c. This will be delta nu half. Okay, if this is given in terms of second, there is no need to multiply c factor, you can directly calculate this. Okay, because it is given in length unit, so I had to multiply c to convert it this into time unit. Okay, can you tell me what is the relation of frequency, wavelength and speed of light? What is the relation between these three parameters? C will be equal to, in terms of lambda and nu, lambda is the wavelength of light and nu is the frequency of light. Anyone? So this speed of light is nothing but lambda times nu. Okay, this is wavelength This is frequency of light. Okay. So are you guys getting what I am saying? Am I audible?
Sir, once you show the question, sir.
Okay.
Yes. This one is full width at half maximum. Yes.
Yes.
Delta nu that is.
Yes.
Okay.
Here. This is the full width at half maximum. So these were unnecessary. These already you know. I just repeated this. So the main formula is this one. You are given this value. This is nothing but delta nu half, and you have to convert it to this angular width delta omega half. Okay, so you have to multiply 2 pi with that. As the unit is in length unit, so I had multiplied c with it. Okay, so effectively I am getting this 1 over 5c, sorry, 1 over 5c delta nu half. Okay, so this will give me directly this natural lifetime. Is it okay?
Okay, sir.
Okay, so next the value is only changing, so you can do this. For B case, this delta lambda half is 1.5 centimeter inverse. You have to just convert it to meter inverse. So this will be 1.5 10 to the 2 meter inverse. This is 150 meter inverse. So you just have to put this in this formula, tau lifetime 1 over 5 c delta lambda half. Okay, so when you put all this, you will get a value 7.1 into 10 to the power minus 12 second. So in this in this time period, 1 over e number of it's not 1 over e number, actually 1 over e portion of initial particles will decay to ground state. Okay, so you compare it. If line width is increasing, the lifetime is also, time is decreasing, means it's decaying faster. Okay, so let's check question number C. It's given 40 centimeter inverse. This is delta lambda half 40 cm inverse. Okay, this is nothing but 4000 meter inverse. Okay, so this lifetime, if you calculate this, you will get, okay, maybe I did some mistake in calculation. Can you check it? Are you doing with me, or you are just watching? check this number. I'm doing this in the next question. Till then.
B is okay, sir.
Okay. So then do the C number. Okay, I have already checked. You can also verify this. You will get this number. Okay. Am I audible? Hello. Hello, am I audible?
Yes, sir. Yes.
Sorry for this internet connection. Very bad today. Okay, so did you get this number for question number C?
Yes, sir.
Okay, very good. Okay, then moving on to the next question. Okay, suppose the collision cross section is approximately equal to the cross section area of atom. Then estimate the collision lifetime of gaseous sodium atom under standard temperature pressure condition. So radius of this sodium atom is given as 0.2 nanometer. Okay, so maybe I am from physics, but in chemistry there is something called collision between the molecules or atoms. So if there are two atoms, let's say, they can collide. Collision is also one kind of interaction. Okay, so there for this collision course also there is some like the collision to happen. It depends on the area of each atom or molecule, whatever you can say. So it depends on the cross section, like maybe did you study it or not, I don't know. Interaction of two point particles, it depends on this cross section. Cross section defines the probability of probability of interaction of two molecules or particles. Okay, so its unit is centimeter minus, its unit is area unit. It's per area. This cross section is defined. Actually, this describes the probability of interaction of two molecules or particles. Okay, if there are two molecules, let's say one have some charge plus q and it has some charge, let's say small q. Okay, so if capital Q is very much greater than small q, then this interaction cross section will be this area of this interaction will be more for this kind of system, because this charge will have influence out of its radius, means whatever its size, but if it has some charge, it will have some influence outside its boundary. So this cross section cross section of interaction, this defines the probability of interaction between two molecules or two particles. So in this question it has been said that this cross section is approximately equal to the cross section of area of the atom. So radius of the atom, sodium atom, is given as 0.2 nanometer. So the area will be pi r square. Okay, so 3.14 times 2 into 10 to the minus 10 square. So this will give you a cross section. Okay, this is approximately equal to the area it's given. So from this we will get this cross section to be 1.26 times 10 to the minus 19 meter square. Okay, now the atom is sodium, so we know mass of sodium is 23 atomic mass unit. Okay, from this we can calculate the mass of this sodium atom. 23 times 1 AMU is 1.67 times 10 to the power minus 27 kg. Okay, if you do this, you will get 3.84 times 10 to the power minus 26 kg. So it's given. We need to calculate the collision lifetime of this gaseous sodium under standard temperature pressure. So what is standard temperature pressure? Under this standard temperature pressure, temperature is 273 Kelvin and pressure is 1 atmospheric pressure or 10 to the power 5 Pascal. Okay. So this collision lifetime, I am just writing the formula, you can check it from the books. This collision lifetime, this will be equal to 1 over cross section times pressure into pi m kb p over 8 to the power half. Okay, so I am not going to derive this formula, you can check this from the books. Okay, so this cross section we have, pressure we have, temperature we have, mass also we have. What is this kb? This is Boltzmann constant, its value is 1.38 times 10 to the power minus 23. Okay, so if you put all these values, this 1.26 temperature is given in okay, it's given in Kelvin 273. Whatever, if you do the calculation, you can apply you can use calculator, you will get this to be 6 into 10 to the power minus 10 seconds. Okay, so like the sodium is in gaseous state, then the sodium molecules or sodium atom, let's say, they are very free to move. Okay, so they can collide with each other. Okay, so this collision frequency, this is measured in terms of this collision lifetime, whose formula is given like this, and it depends on the temperature of the surrounding, mass of the particles, pressure which are in the external sources, and the cross section of interaction. So if we put all the values, we will get the collision lifetime to be this much. Okay, so are you guys following?
Right, sir.
Okay, so no doubts, right? Okay, so let's move on to the next question. Okay, so next question is Mercury has an atomic radius this much, 0.17 nanometer. The transition happens at this line 546.1 nanometer, has an Einstein coefficient A this much. Then calculate the natural Doppler and collision line width for this transition. Okay, so there are two conditions: low pressure and temperature is 250 degrees Celsius, and high pressure and high temperature. Okay, so in week number 5 class you already know formula for this one and this one, and collision line width just now I told you the formula. Okay, so what is given? The radius of this mercury is given. Mercury atom is 0.17 nanometer or 1.7 to 10 to the power minus 10 meter. Okay, and Einstein coefficient A is given 4.9 times 10 to the power 7 second inverse. Then we need to calculate this tau natural, tau Doppler, and tau collision. Okay, so tau natural formula we know, we did in question number 1. So this tau natural if you want to calculate in terms of this Einstein coefficient, we did like this. Like in the formula I told you, nt is equal to n0 e to the power minus 80, and this time we took as tau, which is 1 over a. So this tau is nothing but 1 over a. So tau natural will be 1 over a. Okay, so if you put the value of a, then you will get this tau natural to be 1 times. Okay, so it's 1 over 4.9 and 10 to the power minus 7 or 0. To 10 to the power minus 7 second. Okay, that's 2 into 10 to the power minus 8. Okay, so what we have to calculate?
Sir, in this case, tau natural directly 1 by a we can put here.
Yeah, tau natural is 1 over a, right? This is the
But in the previous case, we have written the formula 2 by delta omega by half.
yeah, sorry. We have to calculate the line width. Okay, so this is the lifetime. So line width and tau natural means this lifetime and line width have some relation, like 2 over delta omega half. Okay, so tau natural will got, we need to calculate this one, line width. So this delta omega half will be 2 over tau natural, right? Tau natural is nothing but 1 over a or 2a, and then you will, this is very simple, you need no need to calculate this actually. Sorry, so this will be 4.9 and plus 7. Okay, so this will be approximately 1 times 10 to the power 8 second inverse. This is for natural line width. Okay, now we need to calculate Doppler and collisional line widths. Give me 1 minute. Okay, so we are asked this natural, Doppler and collisional line width. So we got natural line width, and for Doppler line width in this week number 5 class, the lifetime for sorry, not lifetime, directly line width formula was given. This delta omega Doppler is given omega naught 2 kb t ln naught 2 over 1 Okay, so we have two conditions A and B. One is low pressure, low temperature, and high pressure, high temperature. So this pressure is also given. Pressure is 10 to the power minus 9 atmosphere. Okay, so we can convert this to Pascal unit. 1 atmosphere is 10 to the power 5 Pascal, so this will give us 10 to the power minus 4 Pascal. Okay, so pressure we have, temperature is 250 Celsius, then we have to convert it to Kelvin. 273 plus 250 is 523 Kelvin. Okay, so why do we need this? We need this to calculate this collisional line width. Okay, so let me first calculate this Doppler line width. So to calculate this, we need temperature and this omega naught. Okay, so let me calculate this omega naught first. Omega naught is nothing but 2 pi c over lambda, where this lambda is given. Transition line is given. That means whatever the transition happening, the emitted or absorbed light wavelength is this much. Okay, from that I can calculate this angular frequency of that radiation, which will be 2 pi c over 546.1 to 10 to the power minus 9, and the c is 3 into 10 to the power 8. Okay, so if I put all the values, I will get around 3.45 times 10 to the power 50 second. So this is omega naught I got. Now I can directly put all the values here. Okay, let's go for Doppler first. Omega naught value I got 3.45 10 to the power 15 second inverse, then 2 into 1.38, this Boltzmann constant value, and this is 10 to the power minus 23. Temperature is 523 Kelvin, and log of 2 divided by mass of the okay, mass you have to calculate. What is given? Mercury atom. Okay, so mass of the mercury atom you have to calculate first. The mass of mercury, this is around 200 atomic mass unit. Okay, so you can convert it to kg. You will get around 3 into 33 times 10 to the power minus 25 kg. Okay, so mass you got, put it here, 3.33 10 to the minus 25 times c square. 3 into 10 to the power 8 whole square. Okay, so if you calculate this, you will get this value to be 2 times 10 to the power 9 second. Okay, so this formula is already given in week number 5. I am just applying that formula. Okay, so this transition line is given, that means lambda is given in the question here. So from this I can calculate the angular frequency. Okay, if I got the angular frequency, I can calculate the line width for this Doppler shape. Okay, this is direct formula. I have already temperature, pressure and mass I already calculated. If you put all the values, you will get this Doppler line width to be this much. Any doubts?
Sir, say little bit about Doppler effect. What is Doppler?
Maybe in chemistry this Doppler shape is different, but in physics Doppler effect is like if one source is there, like I am from physics, so I can explain it from physics point of view. So if one source is there, let's say one light source is there, it's emitting light with some wavelength lambda. Okay, and this source is moving with some velocity v, let's say, and you are an observer standing still here. Okay, so or you can assume this to be a car or train making sound, like it's putting some horn and it's moving. So you have already experienced this. If one source is coming, like when train is coming towards you, the sound seems to increase, and when it is near to you, it's like some maximum, and when it leaves from you, the sound seems to decrease. So similarly, when light moves towards you, there is something called special relativity, due to which when an object is moving near to speed of light or at speed of light, there will be something called length contraction. I am sorry I couldn't give you some chemistry point of view of this. Maybe in next class I'll get back to you by chemistry point of view, but in physics point of view, this length contraction will happen when this light is moving towards you. This length will seems to contract, so wavelength of the light will reduce. So let's say you have some wavelength something like 100 meter. So when it is approaching towards you, the wavelength whatever, okay, what you observe, this wavelength is around 80 meter. So wavelength is decreased. That means what? The frequency of this light will increase. Let's say this is lambda 1, this is lambda 2. This is the original wavelength of light, and you are observing this wavelength to be 80 meter because it is moving towards you. So length contraction. So you know speed of light is nothing but lambda times nu. So if lambda decreases, then frequency will increase. Okay, then it will seem like the energy of the particle which is coming towards you is increased. Or by your experience, if you, let's say this is red color of light originally coming, when the wavelength is decreasing, it will appear as blue color light. This is due to length contraction. Similarly, when this 100-meter light is going away from you, the wavelength you will observe will be slightly more, like let's say 120 meter. So in this case, what we say, this light is red shifted. Like red color is having more wavelength. So if wavelength is increasing, so we will call this as red shifted. But when the wavelength is decreasing, we call them as blue shift. Like blue light have some wavelength less than red shift. So in this spectra, blue light will have more energy and less wavelength, and red light will have more wavelength and less energy. So due to this Doppler effect, what you will see, this due to this special relativity case, light wavelength will seem to be increased if it is going away from you, and its wavelength will seems to decrease if it is approaching towards you. So if it is approaching towards you, its wavelength will decrease, so we call this as blue shift. And if it is receding from you, its wavelength will increase, so we call this as red shift. So in chemistry point of view, I am not sure, maybe in next class I will get you some answer about this Doppler line width. Okay, so this was taught in chemistry. I thought you guys already know about this. In week 5 sir taught this about this Doppler line width. So I guess you already know this in chemistry, so I put this problem for you. So it's okay. Next class maybe I'll give you some explanation about this. Okay.
Okay, sir.
Okay, so we calculated this Doppler line width for this low pressure and low temperature case. So similarly, we can calculate high pressure and high temperature case. So pressure is 1 atmosphere, so you can convert it to Pascal. It will be 10 to the power 5 Pascal. And temperature is given 500 degrees Celsius. You can convert it to Kelvin. So 500 plus 273. This is 773 Kelvin. So similar to this, you have to just replace the this temperature, and it does not depend on pressure. So you have to just replace the temperature, then this delta omega Doppler for high T value will go. Sorry, you will get. This is for low temperature. So you have to just replace this temperature in this formula and you will get this number. So I am not doing this anymore. You can try this. Okay. So what we did, we calculated this natural wavelength here, and we calculated the Doppler wavelength here. Now we have to calculate the collisional wavelength. Okay, so delta collision wavelength, this is given as for this one. On over sigma s p under root this pi m k b t over 8. Okay, so in this question, radius of mercury atom is given So from that we can calculate the area, and the approximation we are taking, the cross section is nearly equal to area. Sorry, this is not area, this is Einstein coefficient A. So the approximation we are taking, this cross section is nearly equal to the area of this particle, which is nothing but pi r square. Okay, so r you have pi r square. If you calculate, you will get this rho s. Okay, and what is P? This is pressure. This you got from pi r square. This temperature, you have two conditions: A, low temperature. Okay, this pressure also have two conditions. Low temperature is 250 degrees Celsius or 523 Kelvin, and pressure is 10 to the minus 9 atmospheric pressure or 10 to the minus 4 Pascal. Okay, this is case number A. Case number B, we have 500 degrees Celsius, which is equal to 773 Kelvin, and pressure is 1 atmospheric pressure or 10 to the 5 Pascal. So everything you have. For case 1, temperature you have, pressure you have, and mass of the mercury atom we have already calculated here. Now what remains? This Kb, this is Boltzmann constant, this is 1.38 times 10 to the power minus 23. So if you put all the values, okay, so okay, this formula is for collision lifetime, tau collision. Okay, so this is tau collision. So we'll first calculate tau collision, then from that you can calculate the line width for collision. This will be nothing but 2 over tau collision. So for first case, if you want to calculate, after putting all the values, you will get around this tau collision for case number A, you will get around 3.38 seconds, and if you put all this value here, you will get this collision length around 0.59 seconds. Okay, did you get it?
Yes, sir. Yes, sir.
So this is for case A. So similarly for case B, that means high pressure and high temperature, if you calculate this delta omega collision, you will get this value to be 8.7 into 10 to the 7 seconds. I am not doing all this calculation, you just verify. I gave you all the values, temperature I gave, pressure also I gave. This Kb you have, Boltzmann constant, pressure okay you have, and this interaction cross section is nothing but area of this particle, mercury particle. Radius is given, so you can calculate this also, and mass also we have calculated. We put all the values and verify. Okay, so any doubts so far? Okay, then I'm guessing no. Then we will move to the next question. Okay, the 629 nanometer line, that means this transition line of neon gas has Einstein coefficient A to be this much. Then find the temperature at which the natural and Doppler line width will be same in a low pressure lamp. Okay, so what do we have to find? We have to find the temperature at which this natural and Doppler line width will be equal. Okay, so let me write down the natural line width first. Delta omega natural, this is 2 over delta, or delta is nothing but A inverse. Okay, so this is 2A. A is given, and we have this collision line as omega naught 2 kBT ln of 2 over mc square half. Okay, so what is the condition? These two line widths should be equal. Is equal to delta omega. Okay, so we have to equate these two terms. From that, temperature is a variable, we need to calculate this temperature. Okay, so this delta omega natural is 2A equal to omega naught root over 2 kBT ln of 2 mc square. Now we need to calculate this omega naught first. What we are given? This spectral line wavelength is given. Lambda is 629.9 nanometer, or 6.299 into 10 to the power minus 7 meter. Okay, we need to calculate this angular frequency. Omega naught will be equal to 2 pi nu or 2 pi c over lambda. Okay, now you know c is speed of light, and pi value also know 3.14 times 3 into 10 to the power 8. Lambda value we have 6.299 times 10 to the power minus 7. If you put all the values, you will get 3 times 10 to the power 15 second inverse. Okay, so you got omega naught. What remains? This mass remains. Actually, what is given? We have given neon. This is neon gas. So neon atom is given. So we need to calculate mass of neon. Okay, you can check it from Google. You will find mass in terms of AMU. So you can check it from Google. This is around 20.17 AMU. Now you have to convert it to kg. So 20 times 17 times 1 AMU is 1 AMU 1.67 times 10 to the power minus 27. Okay. Then if you multiply this, then you will get the neon mass to be 3.35 times 10 to the power minus 26 kg. So mass you got, omega naught you got, and every other variables you know. Temperature you have to calculate. Okay, so from these equations we can write this in terms of temperature This will be 2 kBT ln of 2 by mc square will be equal to 4a square over omega naught square. Okay, then temperature will be 4a square. This a is Einstein constant. Okay, this value is also given in this question. mc square by 2 kb ln of 2 omega naught square. So every variable value you have a, m, omega naught we calculated, kb you know, and ln2 is a constant. So if you put all these values, you will get around 2 into 10 to the minus 4 Kelvin. Just verify it. I gave you all the values. Omega naught, a is given, m we calculated here, m is mass of neon atom, and kb is the Boltzmann constant, and every other things are constant. So if you put all those values, you will get the temperature to be this much. So at this temperature, what will happen? This natural line width and this collision line width will be equal. Okay, any doubts? Everyone got it? Okay, let me explain one more. So in this question we are asked at what temperature this natural line width and collision line width will be equal. Okay, so we know from the class all the formulas, like this natural line width will be 2 over tau lifetime, and this tau is nothing but 1 over a. So this becomes 2a. Okay, and this collision line width is nothing but omega naught 2 kBT ln 2 by mc square whole power 1 over 2. Then we equated them and solved for temperature. Now all the variables we need, we calculated the mass of this neon atom, we calculated, and a is given already. Omega naught also we calculated because the spectral line was given, lambda was given. From that we calculated omega naught, and everything is here. So we put all the values and we got the temperature to be this much. Okay, so any doubts? Okay, so I assume no doubt. Moving on to the next question. Okay, in stimulated emission, what is the lifetime of the atom's ground state? Okay, so stimulated. Okay, let's say there are two states, state 1 and state 2. Okay, what is stimulated absorption? Will supply some energy to the ground state particles, let's say h nu. They'll absorb this energy and they'll do the transition to the excited state. Okay, so we are asked what is the lifetime of the atoms in ground state. So the particles staying in ground state, what is the lifetime? So if no energy is provided, what will happen? The particles, they will prefer to stay in ground state. Like if you don't supply any energy, they spontaneously decay to ground state and like to stay in ground state. Okay, so if you don't interfere with this system, that means you don't supply any energy, then they will prefer to stay in ground state forever. So in this question, this for stimulated absorption, what is the lifetime of atoms in ground state? This will be infinity. Okay, any doubts? So it's the tendency of nature, they want to stay in lowest energy state. That is why the particles, they will prefer to stay in ground state. Okay, so the lifetime for the ground state will be infinity. If you don't interfere with them, then the lifetime of the ground state will be infinity. Okay, so no question, so we will move. So in next question, a solution of tryptophan has an absorbance of 280 nanometer. This is a absorption line, and absorbance is 0.54. This is not Einstein coefficient, this is absorbance. Okay, and the line, the length of the covert is 0.5 centimeter. So what is this? This system, it has a length. This means there is a solution. In this, let's say beaker, it has a length L, and one light source is applied on it. Then what will happen? Some of the lights which are applied on this system, some of it will be absorbed by this solution. Okay, and some will be transmitted. So the absorbance of this system, that means if you applied 1 unit of light, then 0.54 unit of light will be absorbed by this system, and rest will be transmitted. Okay, and the absorbance coefficient, let's say epsilon, this is given to be 6.4 times. Okay, there is nothing. Okay, 0.6. Maybe I made some mistake. I didn't write. Okay, let's take it to be 6.4 liter mole inverse centimeter inverse. Okay, so from week number 5 class, you must know the absorbance. It depends on the concentration of the molecule, the length through which this light is traveled, and this parameter epsilon, which is the absorbance coefficient. Okay, maybe we recall it as L over logarithm of L over logarithm of I over I naught is equal to L C epsilon naught, which was equal to this absorbance. Okay, so we are given absorbance, we are given length, we are given this absorbance coefficient. Now we have to calculate this concentration of the molecule. So it's pretty straightforward. So C will be A over L epsilon. Okay. Any doubts? Hello. Okay, we have A, we have L, we have epsilon also. Now let's put all these values. 0.54, our length is 0.5 times this epsilon, 6.4 liter mole inverse, centimeter inverse, this is centimeter, this will cancel. Okay, so if we solve this, we get this concentration, this value to be 0.000168 molarity. Okay, this is mole per liter, this is the unit of concentration. Okay, so I already gave all the numerical values, just put it and we'll get the concentration of the solution. Okay, so any doubts? Okay, let me repeat it again. Then we have a solution. Okay, it will have some concentration, right? So that means amount of solvent in this solution. This is nothing but the concentration of the solution. So what we are doing now, we are putting some external energy or light, we are passing some light through this solution. So by this process, what is happening, some amount of light is being absorbed by this solution and rest is emitted. Okay, so the amount of light absorbed by this solution is determined by this absorbance. Okay, so absorbance is given as 0.54. That means what, around 50% of the light is being absorbed by this solution and rest is transmitted. Okay, and if I increase the length of the beaker, that means the light has to pass through more solution, right? Then in that case more absorption may happen. Okay, so this absorbance, that's why depends on length also, right? If I increase the length of this beaker, then the light has to pass through more solution, so then the absorbance will be more, right? So it depends on length, and if the concentration is more, that means more solvent is there in this solution, then this solution will be thick, right? Vaguely saying, this solution will be some dense solution, right? So if the solution is dense, then it will be more capable of absorbing more light. So it directly proportional to the concentration of the solution, and this A is equated with these two parameters by some constant. We call it as absorption coefficient. Okay, so this is the proportionality constant, absorption coefficient, and this absorbance depends on this concentration and length of the solution with this absorbance coefficient. Okay, so it's straightforward. We have the relation, all these parameters are given, then we have to calculate, this epsilon is given, we need to calculate this concentration of the solution. It's pretty straightforward, everything is given, you just put the values and get the concentration. Okay, moving on to the next question. Okay, so the absorbance of copper sulfate solution contains 0.5 milligram of copper per milliliter, as reported to be 0.35. That means absorbance is 0.35 and the absorption line absorption line lambda is 440 nanometer. Okay, now calculate the specific absorptivity including units for this copper sulfate solution, assuming that length is 1 centimeter. So L is 1 centimeter, and this is concentration is given milligram per milliliter, length is given, C is given, lambda maybe we don't need, A is given. Then we need to calculate the specific absorptivity. This epsilon we need to calculate. Okay, so it's pretty straightforward. A is nothing but epsilon L C. Concentration is given 0.5 milligram per ml. Length is 1 centimeter. Then we need to calculate epsilon, and A is also given. Okay, this epsilon will be A over L. A is 0.35, L is 1 centimeter, and C is 0.5 milligram per milliliter. So if you put all the values, you will get this coefficient to be 0.7 centimeter inverse milligram ml inverse. Right. Any doubts? Okay, I assume no, because it's pretty simple formula. We are just putting all the values whatever we have, and we are calculating whatever we don't have. Okay, so moving on to the question number B. What will be the absorbance if the solution is diluted twice to its original volume? Okay, so if the absorbance is diluted twice, then what will happen to the concentration? So we have some solution. So what is the concentration? This is amount of solvent per liter or per milliliter. Okay, concentration is amount of solvent per liter or milliliter. Okay, so we are diluting this solution. That means what? We are increasing this amount of let's say water. We are making it double. So what will happen? We are diluting it twice. That means we are adding twice the amount of water whatever we had initially. So we are doubling it. So in that case, what will happen? The concentration will decrease to half. Okay, so in that case it will be 0.25 milligram per milliliter. Okay, so C is changed to this value. Okay, now in this case, what will happen to this absorbance? Okay, this is a proportionality constant we have calculated, this epsilon, so it won't change for the system. If the concentration changes, what will happen? The absorbance change, because the solution is diluted, right? Now its absorbance will change for this specific life. So direct formula A is epsilon Cl. Epsilon we have from the question number A. C is changed now to this, length is 1 centimeter. Okay, so if we put all this value, 0.7, concentration is 0.25 now, length is 1 centimeter. So if we put all these values now, this will give us 0.175. So you check this. Initially we had the absorbance 0.35. Now after dilution, what is happening to this absorbance? It's becoming 0.175. So you see, when we diluted the solution twice, that means it's diluted twice, then what happens? The absorbance decreases by a factor of half. So initially we had absorbance 0.35, now it became 0.175, almost half, right? So if the concentration decreases by a factor of half, then the absorbance also decreases by a factor of half, right? Because A is directly proportional to C. So if it decreases by half, A is also decreased by half. Okay. Any doubts? Okay, I assume no. So we'll move to the next question. Okay, the extinction coefficient of this solution, let's say NaDH at 340 line width is this much. So epsilon is 6440 liter mole inverse centimeter inverse. Okay, whereas this NAD does not absorb this line, that means these two systems, NADH and NAD, this NADH, it has a absorption spectrum lambda equal to 340 nanometer. Okay, for this system, this lambda is not equal to this lambda. Let's say this lambda prime is not equal to this lambda. It has some different absorption spectrum. Okay, so it won't absorb this, or it won't emit this wavelength of light. It won't absorb or emit this wavelength of light. Okay. So we are talking about absorbance. So let's say it won't absorb this wavelength of light, this solution. Okay, but this will absorb. So what absorbance will be observed when light at 340 nanometer passes through 1 centimeter of cuvette containing 10 micromolarity of NaDH and 10 micrometer of NAD. So what we have a solution of concentration 10 micromolarity, 10 micromolarity of NaDH plus 10 micromolarity of NAD. Okay, so this solution contains this concentration. Okay, so we are applying 340 nanometer light on this solution, and we have this extinction coefficient to be this much. Then in this case, what will we have, how much light will be absorbed, that means what will be the absorbance. Okay, so it's pretty straightforward. A is nothing but epsilon C L. L is also given, this is 1 centimeter, and epsilon we have, concentration we have. So we have two kind of solution. One is NaDH which absorbs this light, and one is NAD solution which does not absorb this light. So in that case, what will the effective concentration? The effective concentration will be this, right, which will be absorbing this wavelength light. So the concentration will be only, the effective concentration will be only this one, 10 micromolarity or 10 to the power minus 5 molarity. Okay, so C we have, L we have, epsilon is already given. Then in that case, A we can calculate. Epsilon is 6440 times concentration is 10 to the power minus 5 molarity and length is 1 centimeter. Okay, so this will be 6.44 times 10 to the power minus 8. Oh no, sorry. Minus 2 or 0.06. Okay. So any doubts?
No, sir.
Okay. Okay. Moving on to the next question. At t equal to tau, this tau is nothing but lifetime. Which of the following is true for spontaneous emission? So you have two states, state 1 to state 2, sorry, state 1 and state 2. So what happens in spontaneous emission? Particles in excited state, they will jump to ground state and they will radiate some energy. So this is in the absence of any external light. So in the absence of any external light, what happens? The system, which is already in excited state, it will spontaneously jump to the ground state, emitting some radiation. This is called spontaneous emission. Right. So let's say at time t equal to 0, the population of this excited state was n of 0. Right. Now at this time equal to tau, what will happen? Which equation is correct? I already discussed this in maybe question number 1. At this time t equal to tau, the population of this excited state reduced to which relation? Any guess?
Option B.
Yes, right. Option B. This at this time, natural time, what happens? The amount of particles in excited states, they reduce by a factor of e, because this nt we can write as n of 0 e to the power minus at, by this at time t equal to tau, tau is nothing but 1 over a, this will be n of 0 e to the power minus 1. So at this time equal to tau, what happens? The number of particles which were there at time equal to time equal to 0, it will reduce by a factor of this e. So this is the right answer. Okay, good. Okay, moving on to the next question. Which of the following statements about the lifetime of the excited state undergoing spontaneous emission is correct? Okay, so read these 4 options and tell me the right answer.
Option C looks correct.
Yes, right. Just now we told this lifetime is nothing but 1 over a. So when this Einstein coefficient A is large, then this lifetime will be small. So lifetime is shorter for states with larger Einstein coefficient. Right. Good. So moving on to the next question. What is the relationship between spontaneous emission lifetime and the Einstein coefficient A? Just now I told.
Option A.
Right. Good. Okay, moving on to the next question. Which term in the transition probability determine the line shape?
It's option B.
Yes, correct. Option. So this transition probability, it is given by some constant. Then this is omega phi square by omega square. Then this factor sine square, and this transition moment integral. So, right. So when you plot this probability, what you will get? You will see a peak. This peak is due to this function delta omega over 2 omega over. This function is nothing but Dirac delta function. So it will peak at this, let's say, some particular frequency omega. Okay, so this function will look like Dirac delta function. So the shape of this probability, it depends on this functional form, right? All others are constant actually. So the line shape, it depends on this term, right? Okay. The lifetime tau depends on the frequency of light and transition moment integral as which relation?
Option A.
Option A.
Yes.
We are saying tau is directly proportional to frequency and transition moment integral. Okay, so you are saying this there is system. So if I increase the frequency of light, then lifetime, let's say this is
Sorry. It should be inversely proportional to the.
yes, correct. So there is
Yes.
one option which is
Yeah.
inversely proportional. So this one, so you can check it. It is being taught in week 5. So this tau is inversely proportional to nu q, and this is inversely proportional to this transition moment integral. Right. So this is the right answer. Okay, good. So according to selection rule, for the transition moment integral, if it is 0, then which option is correct?
A option.
So if it is 0, then transition is allowed.
Oh, sir. Sorry. No, sir. It should be non-zero.
Yeah, if it is non-zero, then there is some overlap between final and initial state, right? Then the transition will be allowed. For this case, transition will be forbidden. It is 0, that means there is no overlap between initial and final state. Okay, so B will be right answer. Okay, good. Okay, this void profile, this is a convolution of what? This voice profile is nothing but one intensity this is a convolution of two intensities. What are those? Or you can say this void shape is convolution of two different kind of shape. What other shapes do you know?
Gaussian, Lorentzian.
Yes, right. So this void profile, it is a convolution of the Gaussian and Lorentzian shape, or you can say it as a homogeneous and inhomogeneous shape. So this homogeneous part comes from this Lorentzian shape, and the inhomogeneity comes from the Gaussian part, because this Gaussian shape, it comes due to some external factor like temperature, pressure, something like that. Whereas this Lorentzian shape, it comes due to the internal property of the molecule. Okay. So this will be convolution of Gaussian and Lorentzian. Okay, good. Okay, moving on to the next question. We can evaluate A, B and transition moment integral from which set?
From the convolution of the both.
No. So you want to calculate A, B and transition moment integral form, right? So if you consider convolution of both, then Gaussian shape will also come there. That means what? Some external factors like temperature, pressure, they will also contribute. So in that case, it will be very hard for you to calculate these factors directly. So the best option will be Lorentzian shape, because it depends only on the intrinsic property of the molecule. Okay, so it's purely dependent on the intrinsic property of the molecule. There is no external factor involved. So the Lorentzian line shape will be the best to calculate these factors. So this is already been taught in week number 5. Just recall it. Okay, moving on to the next question. The relation between Gaussian and Lorentzian line width is which one?
Option C.
Yeah, correct. See, for Lorentzian line width, it only depends on intrinsic property, so it will be more like spiky when some external factors are involved, like temperature. In that case, the shape will be like somewhat flat. So this is Gaussian, this is Lorentzian. Okay, so what is line width? This line width is the width of the distribution at half intensity. Okay, so what is the half of this distribution at this point? This is the line width. So if it is Lorentzian, this is omega half Lorentzian, and this is Gaussian distribution. This half will be somewhere below. This is the line width for this Gaussian line width. Okay, so you can clearly see the Gaussian line width will always be greater than or equal to this Lorentzian line width. Equal means at some cases when there will be no external factor involved, in that case it can be equal, otherwise it will always be greater than length. Lorentzian line. Okay, good. Okay, moving on to the next question. In a spectrometer, and in a spectrometric cell of 2 centimeter path length, L is given. The solution of the substance shows an absorbance value A. This is A1. If the molar absorptivity of the compound is this much, that means epsilon is given. Calculate the concentration of the substance in the solution. So you have to calculate C. So it's direct formula. A is epsilon CL. So C is A by epsilon L. Right. So A is 1, epsilon is 2 times 10 to the 4, length is 2 centimeter. So it's 1 over 4 times 10 to the 4 minus 4, or 0.25 10 to the 4 minus 4, or 2.5 10 to the 4 minus 5. Okay, it's pretty straightforward. So this is the right answer. Okay, this was the last question. Okay, so time is over. I didn't do everything numerically. I gave you the value and finally told you the answer. So what you do, you multiply all these values and verify all this. Okay.
Sir, can you please let me know how the final exam pattern will be, like subjective or objective or problem solving?
Actually, I don't know. I am KMR fellow, so as I can observe, sir is always giving some multiple choice question. Probably this will be multiple choice question, I guess.
Even the final exam?
Yeah, maybe. I got some notification about live session with sir. So did you join that?
No, maybe I missed the live session thing.
Uh,
I didn't.
Maybe he
Um,
can answer it better.
okay, sir. Next time, if I get the live session with sir, I'll definitely join.
Yeah.
In case it doesn't happen, in the next session, can we discuss about this? Can you please let us know?
Okay. Okay. I'll ask sir. If he replies, then I'll let you know. Okay.
Okay, sir. Okay, sir. Thank you.
Okay. Then see you in next class.
Okay, sir.
Okay. Then good night.